And welcome. In this video we're going to be talking about sets of sets. Now previously in the other video we've talked about sets in general, so sets or sets like A are some sort of collection of objects. So objects X. Okay, so we say that X is in A. All right. Now, and of course, you could have, a universal set. X of all allowable objects. Objects X, and the idea here is that X, these little objects, are always an element of our universal set, and the question then, of course, is X an element of A or not? Not an element of A. Okay, so that's a basic question we might want to ask, and that's the fundamental question of sets: is an object in a set or not? And so that's the general framework we have for dealing with sets. But then what we might want to do is now just make a higher order generalization here and now talk about sets of sets. Okay, so we're going to use script notation for this. And we're going to use the same brackets too. Okay, so we're going to use brackets. So we'll use script notation A, and I put that little curl on that and that curl there. And that's going to be a bracket, and it might be something like this, where there'll be a set of sets. So A1, A2, A3, A4, and so on, something like that. And the idea here is this is a set of sets where these are all sets. Okay, so typically, we call these collections. So we'll say A is a collection of sets. So a set of sets is what we call a collection. S-O-S, set of sets. Okay. So this certainly is a higher order generalization of things. So I'll just give a kind of a basic example. If I say oops. So I'll say A1 is just going to be equal to the set of 1. A2 will be the set of 1 and 2. And then A3 is equal to 1, 2, 3. And then we make a collection out of that. We use our script symbol, and that'll just be A1, A2, and A3. All right, so now we have a higher order generalization of these ideas. One thing we cannot say, so don't do this. An object cannot be an element of a collection. Don't do that. Okay? The only objects that are allowed in a collection are sets. So we can say that A is an element of our collection, but not an object is an element of a collection, even if X is an element of A and A is an element of our collection. Okay, and that's very key. So objects of the base sets, i.e. A, cannot be members of our collections. All right, so it really is a higher order way of thinking about things. Okay, so let's now talk about operations. On collections. Okay, so of course there's intersection. And there's union. Okay, and so we give these symbols. So again, if I have some collection, right, that. Now I want to take an intersection. So I say I take a big intersection symbol and I put it next to this. And the idea is that this produces a set, not a collection. All right, so let's go to our example again of A being the collection of sets. 1, this is A1, and A2 was 1, 2, and A3 was 1, 2, 3. So there's my collection of sets. And then, of course, the intersection. So this intersection, what this means is intersect all sets in the collection. That's what this symbol means right here. Okay, so let's do that for our example. It's pretty straightforward to see. What we do is we intersect the first two sets, and of course the common element in both of those is 1, and we intersect that with the third, and the common element between all three of them is of course 1, so the output set is simply 1, or in this case we can also say A1. Okay, in this particular example. Okay, that's pretty good. And of course the union, it's the same thing. We write it like this. And of course means union all sets in our collection. And of course for our particular example here, if I union this one and this one, I get 1, 2, and if I union that to the third one, I get 1, 2, 3. 1, 2, 3. That's the answer there, and that of course is equal to A3 in that particular case. Okay, so this makes pretty good sense. Of course, it gets more complicated. When either the A's or the collection of A's are infinite. Okay, and that's where it gets more complicated, and we'll see that this is a really fundamental idea of how to union and intersect infinite sets that themselves might be each constituent set may also be infinite, infinitely sized. So that kind of case is much more complicated. Obviously, with these finite sets here, these finite sets, it's fairly elementary how to do this thing. So let's go to some more examples of this type of thing. So before we do that, let's go to we got to establish some more notation. And that is the notion of indexing. Okay, so indexing. Let's refer back to summation notation. So let's go back to before you enter this class, you want to look at some. And it works a lot the same way. And the idea is if you have a sequence of numbers, like A1, A2, A3, all the way to AN. Okay, and of course the sum is going to be equal to the sum, that big sigma symbol, from n equals 1, and that's sort of from, to n of AN equals what we'll call our big S, some result. Okay, so of course this is equal to A1 plus A2, dot, 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 all the way to AN. Likewise, we could also, if a1, if it goes all the way to an and then it goes all the way to infinity, so if this is infinite, then of course we write the sum s, if it converges that is, n equals 1 all the way to infinity of an, and that equals my, my sum. Alright, and of course this is an infinite series. We've seen these things before in calculus and we're very aware of it. But the idea here is that each one of those subscripts there represents an index. And we're very familiar with how that works. Okay, so this sum that we've picked out, and we have this index. And the idea here is we want to do the same thing. Yet another way to write this, though, is to say that we can say the sum is equal to the sum. And rather than having a from and then a to, so here we have we start at the bottom, and then the upper notation is 2, and that could be, of course, going on forever to infinity or stopping at some finite natural number. But we could simply say that n is an element of the natural numbers, okay? And then to say we're going to sum an over all of the natural numbers, and that just says what this symbol here represents then is sum all an where n ranges over the naturals. Okay, and this notation is a little bit more abstract, but it also is a little bit more compact, and this is really I wanted to give you this concrete example involving summations before we go off to discuss what happens when we index now our sets of sets. Okay, so now we go to A. We talk about our script A as our collection. And we might write it like this. Sets A, S, where now S is some index. And this index is part of some index set, which I'll call capital S. You know, an example then, of course, would be so S, for instance, is this S represents our index, and that capital X is our index set. Okay, it's the set of things that we're ranging over. So an example would be S is equal to the natural numbers, just like we saw previously. Or it could be finite. So it could be that S is equal to some finite number of numbers, 1, 2, 3, all the way to n at some stopping point. Or it could be infinite and uncountable. It could be that S is equal to the reals. All right, in which case there's no discrete way to write down what we're doing here, but so basically what you have here is a set of sets that are indexed by some real number. Okay, so let's give some examples of the type of things that we see here. So the type of things that can occur here. All right, so the example we want to give first is of just going to our basic finite case. So let's give an example. Let's now talk about S is equal to the set 1, 2, 3, all the way to 4. Whoops. And of course, our collection of sets was equal to 1, 1, 2, and 1, 2, 3. That's our collection. And of course, if we've already computed this, but another way to write this, if I want to write this index now, I can write it like this, but now I can also write it as pardon me, I'm a little sick today. We can write it as index. So we can now write this as A1, and that's A2, and that's A3. We can say S is an element of the set 1, 2, 3, and we're indexing S like that. Okay, yet another way to write it would be an index S is equal to 1 going to 3 of AS. Okay, all of these are similar, and of course we know that the result will be just 1 because the intersection of all three of these is just the set 1. We can do the same thing, of course, for union, but I won't belabor you further with that. Okay, so now let's go on to an infinite case. Okay, so infinite case. And so we can do a pretty straightforward, well, I wouldn't say it's straightforward, but it certainly is. Now let's go to an infinitely indexed set. So I'm going to talk about A being the collection of all sets, which is real intervals. Real intervals, S, starting from S and going to 2, and it's a closed interval, where S ranges from 0 to 1. Alright, so I'm going to put that in my brackets. I'm going to put that, make that the subject to condition. So this is the types of intervals, this is the type of object we're considering, subject to the condition that S ranges from 0 to 1. So let's just give some examples. So what are some of the objects in this, what are some of the sets in this index? So let's say if I have AS, then that could be some object S2. Okay. Now again, pardon, I'm a little sick. Okay, so AS, and this is an element of our collection if S, this index here, is a real number between 0 and 1. Okay, all right. So there's an example, and now let's go through some basic calculations. Let's talk about how to do a basic calculation on this. So let's now talk about the intersection. Now, when you're going to intersect my collection like that, right? What is the answer? So this is a pretty interesting thing. So I don't know the answer quite yet, but let's see if we can write down slightly different notation. I can write S as an element of the unit interval, right? That's because that's our condition there. So we're going to range over those values, and I'm going to put here then the types of sets in this that were in the collection. So it's going to be S, comma 2. All right. So this seems pretty good. All right. So the intersection, of course, has to contain elements. So first of all, X is an element. The objects that are in this intersection of the collection, if X is an element of S2, the interval S2 for all, and I'm going to put my for all symbol there, for all S and in the element from S values in the range 0 to 1. Okay, so clearly S being in 0 to 1, that's less than 2. So really the least upper bound here would be if I take S is equal to 1. And so of course we clearly see if you just visualize this sort of thing, and I can write this out here. It starts at 2. There's 1 right there, and our intervals are always in this range, and so we can move S along this value here all the way from 0 all the way up, and all of our sets kind of look like that. Okay, so they move up and down here. Of course, x has to be in it, and that means it has to be in all of these sets. So of course, the x's always have to be over here, because if I pick an x here, of course, I can always find an s value that's bigger than it, in which case that would exclude those objects that are all down there. So the result would have to be, visually, you can just see it, it has to be the interval, the closed interval 0 to 2. Okay, so that's the result. And of course, the other way to write this is, I can write it like this: s from an element of 0 to 1 of the sets s, intervals s to 2, and that's equal to the closed interval 0 to 2. Okay, so and of course, an object is in this set when it's in all of them. If x is equal to 1, that's okay, because x equal to 1 is always bigger than the lower bound s. Okay, so now let's go to the example then. Let's go to the final example now of taking our same set, our same collection of sets, which is going to be intervals of this form, subject to the condition that s is in 0 to 1, in between those 2 points. All right, so that's my collection. Now I want to do the union. Okay, so I want to look at the union of this collection. All right, so this looks like it might be a little bit more interesting. And of course, this is going to be the set of all points. The set of all points where x is an element of AS, subject to the for all s elements of 0 to 1. Okay. I should actually, I'm going to be a little bit more precise here. I'm being a little vague. That's not quite right. For some s in 0 to 1. Okay, it could be any s, and of course this is a larger set than the intersection. All right, so the question then is, all right, again, let's draw out this number line here. We have 2, and then there's the 1, and then there's 0 there. And the sets that are in the collection are all these sort of these intervals right here. They range there like that, like so, as follows. So if I pick this x here, I say, well, can I find one of these intervals in my collection that includes that? Okay, so again, pick x anywhere from anywhere inside from 0 to 2, and can I find a set that oops, I'm being a little imprecise here. I'm going to pick an x in the range 0 all the way up to 2. Okay, and it seems like that does it, because I can always find, so if I can, then I can always, you know, pick s less than x, and then I can find as that x is an element of that as. Therefore, x is an element of my union set. So the question then is, and the big question is, what about x equal to 0? Okay, is x equals 0 in there? So and the answer is no. And that's a pretty clear answer, because I can't find s less than 0 such that, and I use the symbol st with periods there to represent such that as actually, x is contained in as. So x is not contained in any as if x is equal to 0. Therefore, 0 is not included. Likewise, what about, another question then is, What about x is equal to 2? Oops. Is that a member of this union? And the answer there is pretty clearly yes, because 2 is included on that. In all of these sets, 2 is included, therefore it is included. So we conclude from this that the union of my collection, which I can also write this way, the union S, an element of 0 to 1, of all my AS sets, okay, these are my AS right up there, is going to have to be equal to the semi-open interval 0 to 2. Okay, so there's an example of how to do a union and an intersection of an infinite collection of sets. Okay, so I hope this accomplished some computations and how to perform the types of arguments we need. But it always boils down to here is to picking x's and asking the question, is it a member of the set or not? And then going through the definitions of the unions or the intersections and seeing if you can evaluate it for a whole bunch of these cases. So how you define sets is by asking, are objects members of sets or not? And if you're considering a collection of sets, you have to be able to have some sort of systematic way of going through all the sets that are in the collection and answering that question of, is X a member of the resulting set or of the resulting intersection or union of sets? Okay, so it's always the same binary question, is it a member or not? And that's how you go through these analyses. Okay, so in later videos we're going to talk about functions. Thank you very much.